Hello everyone, my name is Ahmad Othman. I'm from OU Tulsa campus. I'll be presenting to you my project in solving partial differential equations, namely Navier-Stokes equations using GPU. And this is to model pipeline flow of incompressible oil products for leak detection purposes. Our outline would be first, we will discuss the problem we have. We will discuss the importance of pipeline flow modeling. What does that mean for leak detection? What are the Navier-Stokes equations? Then we will have a formal problem statement, and then we will outline the challenges of this research. During this, we will show a little bit of related work, and then we will have a dedicated section for related work. And then we will move to parallelization strategy and optimization, and then we will jump to the evaluation. Pipeline modeling is a short name for pipeline flow modeling. It's important for many reasons. Operation optimization, simulating operational transient states, pipeline controller training. When you have a simulator, you can train your pipeline controllers on real or kind of pipeline-like situation. Also, you can have a leak detection system when you have a flow in and flow out, but you don't know if the pipeline is leaking or not. This would tell you based on pressure, temperature, and other values readings. This would tell you if there's a leak on the pipeline. You can also product batch tracking and know every batch because there are a lot of batches in the pipeline, and among other benefits of pipeline flow modeling. Okay, why leak detection? PHMSA is a federal agent that is with the U.S. Department of Transportation. They announced that since 1986, we had about more than 8,000 significant incidents in the U.S. So significant means that these incidents that involve death, injuries, and economic severe harm. This will average to be about 300 incidents per year, about an incident every 30 hours. During the last year, we had 20 deaths, 117 injuries, and over 256 million in damages. Number of fatalities since 1994 is about 362 people lost because of leak incidents, and we had a total of $6 billion of damages because of these leaks. So we understand the importance of leak detection. Now, what is the basic foundation of leak detection? There are multiple modeling schemes for pipeline flow. The one that proved most valuable is Navier-Stokes equations. Those are partial differential equations that are widely used to model every single flow, actually, whether air or liquid. Many applications exist for them, like weather, wind current, liquid flow in pipeline, aviation airflow, vehicles airflow, among many others. Okay, let's give a mathematical background about the computational fluid dynamics. Equation 1 is the first equation of Navier-Stokes equations for incompressible flow. We see here that the derivation of flow velocity is the divergence of flow velocity multiplied by flow velocity minus the pressure at that location, x, y, and z, plus the viscosity multiplied by the Laplacian of the flow velocity, in addition to some other forces. These are defined, but I don't want to go through them right now. Here, this is a picture courtesy of a website that does the pipeline modeling. We see that normally the flow velocity is really high in the core or center of the pipeline, and it goes less and less toward the walls of the pipeline because of friction. Our problem statement. Leak detection system suffers from low number of modeling points, and this is by design because leak detection systems has to be real-time task. So the number of partial differential equations that represents the modeling points are limited to what CPUs can handle. So they reduce the accuracy of leak detection systems to fulfill the requirements of being real-time. Okay, what are the challenges of this research? Most of the numerical methods were presented to solve PDEs were kind of presented in the previous centuries, or like 1800 and 1900, and they were not designed to do parallel work. They were just designed to solve a problem. Recently, these researchers started to optimize and parallelize these numerical methods solutions, but none of these numerical methods or took some leak detection aspects in consideration. Also, the challenges of this research that requires a huge time um, for the learning curve of it, understanding the science behind it, and then understanding the open source or the code that exists in there. But there are also abundance of attempts to tackle this problem. What is our contribution in this work? It's our parallelization strategy, and to the best of my knowledge, there is not in the literature any study about Navier-Stokes equations solvers for real-time PDEs that serves the services of leak detection. We try to perform some domain-specific tune-ups. We focus on liquid pipeline modeling accuracy needs by reducing the computation load and reducing memory usage by finding any opportunity for binning. Also, we try to present a tailored variable size for pressures, temperatures, among other variables needed in the equations. What is the motive behind this parallelization strategy? One, instrumentation error ranges on incompressible liquid pipelines are not that impressive. For example, the error in the state-of-the-art pressure sensors and transmitters can be lower than cannot be lower than 25 per 10,000 of a full scale. So that can reach up to minus plus 10 psi out of value that's 4,000 or 3,000. Or actually, most of the pressures we see in the industry is not more than 1,500 psi. So we need a tailored tailored solution that meets the industry needs. Okay. OpenCurrent is a free and open source software. Its architecture is flexible and built around reusability. It is built in layers and it's widely adopted and used by many researchers. OpenCurrent is developed by David Common, and he works for NVIDIA Research. Serial methods to solve Navier-Stokes equations are abundant. OpenCurrent started from a famous serial implementation. I'll be highlighting it during my presentation. And I will highlight also the difference between the serial method and the parallel method. We've seen this, just a reminder. We have two equations for computational fluid dynamic pressure, the computational fluid dynamics for Navier-Stokes equations. And those are the two equations. One says the divergence of flow velocity equals 0, and one to calculate the momentum of flow or by deriving it. So here we have the time marching algorithm where we say that flow velocity at time t plus 1 is flow velocity at time t plus the differentiation of flow velocity in regard to t multiplied by delta t. Let's plug equation 4 and equation 1, the one we know, and then we will have this term. Now, let's take minus the pressure out, and we will have a u hat. And that means u hat equals ut plus 1, or ut plus 1 equals u hat minus minus delta t multiplied by p. From equation 5, we can plug the second Navier-Stokes equations from pressures limit, which is equation 2. That means the equation 2 of Navier-Stokes says that divergence of u equals 0. That means the divergence of u equals 0 at any time. So we can plug equation 5 in equation 2, and we will have this equation 6, and which will be the basis for our solution. Because when we solve for pressure, we can find the flow.
The basic time marching algorithm. Input u at time t0, either from boundary conditions or from sensors on the pipeline. Then we will calculate U at times T1, 2, 3, etc. From equation 6, we have to solve for P, and this comes from the fact that the Laplacian of P is this right-hand side. Let's only focus now on the Laplacian of P, and let's focus only on the x component of it. The x component of it could be written this way, and if we want to take an example at point 4, that means we're going to be P5 minus P4 at delta x, distance between them, and P4 minus P3 at delta x. And this equals the x component of the Laplacian. This looks like a stencil computation, so all the optimizations that can be applied on the stencil computation could be applied in here. To find the pressure on the whole on the length of the pipeline, this looks like a sparse linear system where all the empty cells are zeros, and this equals the right-hand side. To solve this, we have the serial version of it. So as we said, the iterative Poisson solver is the one that tries to solve the sparse linear system, but in a serial way. And this happens like by having the matrix multiplied by P equals an R, and then equals the right-hand side. Then we start by having a guess, let's call it P prime, and then until the error is less than a tolerance, we keep updating P prime. But this is extremely serial, so we go to the serial Gauss-Seidel relaxation method. We start by rewriting the equations to look this way, and we have P0, P1, P2 to be calculated, and this, in order to calculate P2 you need 1 and 3, in order to calculate P0 you need 1 and 7, and then at time T1 you calculate P0, then P1, then P2, all the way to P7, and then time 2, and this is still serial. To parallelize this, David Cohen with NVIDIA recommended what to be call it, the red-black, what to be called red-black Gauss-Seidel relaxation, like chess. So, and we have odd and even. So for each even equation, solve, and for each odd equation, solve. And this turns it to be two different for loops that extremely dependent from each other, independent, from each other. And so you have here P0 dependent 1 and 7, 1 and 3, 3 and 5, 5 and 7. And if you notice here, this is extremely cache friendly, as 1 will be brought, and then the next calculation will depend on 1 and still there, and then 3 is still there, and 5 is still there. So you only basically have one global memory access, and then the rest will reside even in the cache. Similar thing for the odd numbers. As I said, we have two threads here, one to calculate P1, one to calculate P3, and there's a lot of reusability in cache in there. Okay, what are the optimizations attempted, and what ideas do we still have? I attempted to implement shared memory tiling. However, this gave me many problems, and now my kernels are not being launched. David Cohen stated that he wasn't able to implement that, and that's really a very complex scheme to use this. But I'm still going to try to do it. Also, I have an idea to compress parameter sizes to meet real life parameter sizes, because, for example, for temperature, we don't have less than 100 minus 50 Celsius to 120 Celsius, and we need only one digit after the decimal point because of equipment error. Also, for pressure, we don't need more than minus 50 to 7,000. This is the maximum worst case scenario. You don't have less than minus 20 or 30. And then pressure, we don't have more than 3,000 maximum pressure measurements, but you can put up to 7,000 just in case of ruptures, or pipeline ruptures, I mean. So here you have 11 bits for temperature, 13 bits for pressure, and we don't need more than one digit after the decimal point. Also, flow meters cannot be more than 40,000 barrel per hour, and no less than 0, cannot be negative. Um, as we said, shared memory tiling and thread coarsening could be an optimization that applies to the Gauss-Seidel relaxation. They already implemented thread coarsening when you can do when they did the odd in one thread, negative even in the other thread and another thread, and then they divided between that, and then for shared memory tiling, it's under implementation. Now we're going to jump to the evaluation. This is the naive version of the versus the serial Fortran. So with a resolution of 64 by 64 by 32, this was the 24 milliseconds versus 47, and we got up to 8.5 times when we had a larger grid. I don't have access to the serial Fortran version, but this is published results by David Cohen from NVIDIA. Also, from single to double precision, they provided this provided about 1.49, and the solution was almost the same. I would like here to thank the subject experimenter Vlad Kundas to help me understand some of the modeling aspects of the incompressible flow. He had more than 30 years of experience in developing and maintaining incompressible liquid pipeline models for leak detection purposes. He developed one of the earlier industrial grade numerical solution for Navier-Stokes equation in Fortran. Thank you for listening, and please send me any questions.